Hi, my name is Scott Thumlert, and I'm working with the Applied Snow and Avalanche Research Group at the University of Calgary. And this short chat is on bridging and its effect on slope stability. So bridging is a little bit of a maybe controversial term, and people have different theories about how it works. And to illustrate that, these are a few excerpts from the Avalanche Review, which is the kind of avalanche journal or newspaper for the United States. And this is like an email discussion that was going around between a bunch of avalanche heads down there. And the first guy says, "I hate the word bridging. There, I said it gives me the creeps." So some people don't like it. He goes on to say, "A bridge has nothing to do with stability or instability." A response from another guy says, "This doesn't make sense to me. If it takes a bigger trigger to release, then it's more stable." And this guy kind of sums it up maybe more appropriately for this talk. He says, "The mistake we make when we're talking about bridges is probably one of load attenuation. A thick slab attenuates the trigger stresses on the weak layer." And that's really the topic of this talk, is how much snow to bridge a weak layer, or maybe how much snow does it take to attenuate that stress underneath a skier. So the first thing to do is we needed to turn the snow cover, the snowpack, into a number, so to quantify it. And in order to do that, we use this thing called the bridging index. And it's simply the thickness of the layer multiplied by its hardness. And so we'll just do a little example. If you wanted to get the bridging index at this red line down about 60 centimeters, you would take the bridging index of layer 1, 2, and 3 and add them together, 1, 2, 3, and each of them thickness times its hardness, and the hardness on a linear scale, and we come up with a total bridging at this line of 130. So that's how we kind of change the snowpack into a number. So when we're talking about bridging a weak layer, we're talking about safety. So how much snow do we need to kind of make the slope stable in relation to skiing? So we're going to use this skier stability index as a proxy, super simplified idea of slope stability. And before I lose anyone, or if anyone's not familiar with this, the top is strength of anything, basically. In this case, we're talking about snow. And the bottom is stress. So if the strength is bigger than the stress, then we shouldn't see any failures in the weak layers. And that number, SK, will be greater than 1. Whereas if the stress is larger than the strength, then we should see some failures in weak layers, and that SK will be less than 1. And Bruce Jameson, in his PhD thesis back in 1995, he did a lot of work with this skier stability index, and he found that between 1 and 1.5, the slopes kind of surrounding where he was doing his measurements would go from more unstable to stable. So we're going to use this 1.5 as a line where we kind of move from unstable slopes to stable slopes. So quickly to describe all the terms in this equation, the top is the shear strength of buried surface hoar, and the data for that comes from a study back in 2006 at the university here, and it just comes from a bunch of measurements of surface hoar layers. This term here is the shear stress from the slab. So this just comes from statics, so it's the weight or amount of snow above the weak layer is putting some stress or force onto that weak layer. So that's that term. And the final term, this triangle here, is the shear stress from us. When we go skiing or snowmobiling, we're adding stress or shear stress to the snowpack. So that's that term. And really, this is kind of the guts of the work that I've been doing at the university here, is we've been using sensors and going out, the sensors are mounted here onto these long aluminum sheets. We've been going out and digging snow profiles and inserting the sensors into the snow cover, and then skiing over top. We've been snowmobiling over top. We've been kind of falling on the sensors. We've been walking any way that humans kind of impact the snow cover. But in this talk, we're going to be mostly focusing on skiers. So this is kind of what we're getting. This is the data that we've been collecting. And what we're looking at here is the measurements for snowmobile stress. And you see snowmobile penetration at the top here, so it's a bit of a difference. And on the left here is kind of all the days with a softer snowpack grouped up here, and the days with a harder or more supportive snowpack down here. And you can see these kind of hypothetical snow hardness profiles there. And so you see right away a bigger, brighter red, so more stress in the softer snow compared to the harder snow. And so this is kind of a qualitative result. We see more penetration and deeper bulbs. And now we want to take that kind of qualitative thing and turn it into more of a quantitative analysis with the bridging index. So back to our equation. So now we have all the three terms, and we're going to plot them on a graph. So here again we have the bridging index on that one side. And if you could imagine the snow cover or zero, surface of the snow right here. And as you're going deeper into the snow, you're getting more bridging, more snow. And the gray here is the stress from the slab and the skier combined. So right away we see the stress in here is mostly dominated by the skier, and it's reducing as we get deeper. So the stress from the skier is attenuating quickly with more snow, more bridging. And then as we get down here, it starts to kind of swing back, and that's because the stress from the slab is starting to dominate. And as we get deeper, more snow, then there's more stress on the weak layer. So now we're going to add in the top of that equation. The red is the strength of the surface hoar. And so as we get deeper into the snow, so if the surface hoar is on the top, it would have a zero strength. And then as we get deeper, we get more weight, it's getting older, starting to bond, there's more pressure on the weak layer, so it's gaining strength. So as we get deeper and older, it's gaining strength. And so if we divide the red by the gray, we're going to get this line here, which is that SK. And if you remember when we talked about, what we're really interested in is this SK when it was 1.5. And so we follow that up and see where our SK crosses this 1.5, merging from, say, unstable kind of slopes to more stable slopes. And it's a bridging index of 130. And, that's a lot of numbers, a lot of data. There's a lot of scatter. So maybe we want a little bit more of a safety factor, or to be a little bit more conservative. And if we go down, say, into the 200 range, we see a good maybe separation between the gray and the red. So this little analysis, these experiments kind of give us this maybe skier stable range of bridging index of 130 to 190. So back to the main topic, how much snow do we need to bridge a weak layer? Maybe 130 to 190 from that analysis. So now we're going to take it a little further away from graphs and whatnot and look at actual bridging index values from avalanches, from skier triggered avalanches. So we're looking at 77 of them, just skier accidentals and ski cuts, all bigger than size 1, so not the really small ones. And just to note, 8 of them were at the actual trigger point of the avalanches. The other ones came from more on the crown or away from where it was actually triggered. And so here's just a frequency plot of those 77 avalanches. And if we look at our 130, which came from the last analysis, we kind of see, about here. So most of the avalanches had a bridging index less than that. And if we look at our 190 or 200, the vast majority had a bridging index less than that. So that's good. That's kind of backs up our last analysis. And furthermore, a lot of those data that we just looked at would be from profiles at the crown. So in this example, the trigger point, or the place where this avalanche trigger, was probably here in the thin spot by the rocks. But as you can see, we're getting profile information from thicker parts of the slab. So those data that we saw in that frequency plot would probably actually be a little bit less than what they're showing. So, and then if we look at the 8 that we got data right from the trigger point, they all had a bridging index of less than 130. So that 130 is kind of backed up by a couple different investigations. Okay, so we have these two numbers, 130 to 190, and we're seeing some data that points us that way, but we do need to be very careful and very cautious when applying that in the field and thinking about it, because the first one is that if you remember the frequency graph, most of the avalanches were on the lower side of that, but there were a few on the outside that were bigger. And so if we were to trigger an avalanche that had a bigger bridging index, that means more snow, which means a bigger avalanche and a higher consequence. So we need to be careful of this, lower probability, lower chance of triggering, but if we do, it's a higher consequence. And then the other thing is the spatial variability, the variability of the snowpack across the terrain. So, for example, on the coast in Canada, we have a much thicker, more uniform snow cover, and maybe this kind of analysis applies more there, because you can maybe do a quick profile, see 130, and then think that, well, that's probably more uniformly distributed across the terrain, where in the Rockies or around here in Kananaskis, we get a lot of wind, a lot thinner snow cover. So in one spot it might be 130, in another spot it might be less, and you could trigger it at the lower spot, and then it would move out into the thicker part of the slab. So we need to be very careful and cautious applying this. And along that same line, I'll leave you with an analogy from that original news kind of article that those excerpts came from. And it's an analogy between computers and bridging. And they say that maybe we don't really understand the complex way bridging slabs and computers work, but we can use them as tools for a decision-making process, as long as we remember that the more faith and information we put into them, the greater will be our disappointment when they eventually crash. So thank you very much for listening, and if you have any questions, feel free to contact us at the University of Calgary.